the syllabus. We will look at these in a little more detail when we get there. I am not going to do the birthday problem right now. We did it in 101, but the punchline on the birthday problem is that in about 300 years we're consuming 3 billion years worth of fossil fuels. And if you're a 100-year-old person, you're 50 million minutes old, and so the ratio there is 10 million to 1. So 10 billion divided by 300 is 10 million. 50 million divided by 10 million is 5. We're in the middle of a 5-minute fossil fuel party at the end of your 100-year life. We're at minute 2.5. Going out with a bang. So that's what that problem is. Okay. And now these are all 2016, 2015. In the bad old days, these were going up as iTunes U, and they were hard to find, and it's all YouTube. So that was lecture 2 of 2016, I think. This guy, we'll do this sample problem in the we'll do this sample problem in the third half hour. Let me just peek ahead here. I might have, oh, you know what? I might have, let me just look. I just want to find exam 1. Okay. Exam 1 is down there. I will move it up. Anyway, I'll launch exam 1 as soon as we've covered the first 3 chapters. That's where it'll be. Okay. So let's just take a look at the book. I think I've got the first 4 chapters right here. There's Boyle chapter 1. And so it's the same group of authors. So the irony or point of this very first paragraph is that, yeah, the sun's been shining a long time. It's very powerful. It used to be all we used. In fact, there's even discussions that the reason the Roman Empire collapsed is they just sort of like mowed down all of the agriculture and just ate their way through, across the globe, and they were just consuming energy faster than the sun could really replace it. And then once Industrial Revolution came, like, oh look, there's a lot more underground. But now, as we consume that, the renewables become more modern. They sort of come back. I don't know if we're going to see actual windmills and things of that nature, but the point is they're coming back. Okay, so obviously solar radiation in its direct form, heat, light. Indirect means that the photon hit the plant, photosynthesis happened, and now you have a carbon bond that will recombine with the oxygen that the plant gave off to give you the indirect. Yeah, and it's weird to think about, but it says when our ancestors first used fire, they were harnessing the power of photosynthesis. So, burning wood that was actually built from the sun, more or less. I mentioned the Industrial Revolution. That's when we really, started going after these deep fossil fuels. And as we know, concerns about the environmental implications, air pollution, people dying in mines. Not really until the 70s, the oil crisis. As it turns out, you probably saw this when we talked about Hubert. Oil peaked on the North American continent early 70s, and right after that, the folks in the Middle East used to let plenty, kind of had us where they wanted us in terms of, you know, scarcity and economics. Here comes nuclear. We talked about that a lot, and there were hopes, of course, that it was cheap, it's plentiful, good alternative. But then, you know, then Chernobyl happens, then Fukushima happens, 3 Mile Island happens. There's no perfect technology, right? Nothing's free, and there's always a downstream, waste being an issue. Okay. So the authors use the word sustainable. Again, that 4-to-1 ratio and that 10,000-1 ratio comes right back. Not substantially depleted by continued use. Geothermal is one. When we get to geothermal, we're going to talk about the fact that you actually can pump heat out of the ground faster than it comes up. In the same way that you can like pump water out of the ground faster than the water table will rebuild itself. So, you're sort of, you know, floating along at a proper consumption rate. And again, you're not going to have significant downstream effects, you know, the externalities as they're called, and then health hazards or social injustice. You know, sending somebody off to the mines, to the neodymium and lithium mines, so you can drive your Prius, right? So there's your kind of social issues as well. Okay, nothing's perfect. Explicit definition coming up in section 1.4. Now, here's a little blaze through Newtonian physics. And let's see, I do not have my slick little pad, but I will try to write on the board. I'm just going to sneak it right down here. Tell me if you cannot see it whatsoever. But here's the key thing. So force. Is that okay? Force? Yep. Good enough? Close enough? Okay. Equals mass times acceleration. If you break that out into dimensions, you've got m for mass, acceleration is length, and that's divided by time squared. So that's how to think about force. And it's always that. Yeah. There's a way to hop between electrical and mechanical, but we're just doing mechanical for now. Energy equals, it's the same as work. Energy equals force dotted into distance. So I've got F dot D. Force is a vector. Displacement is also a vector. So, for example, this is a classic example. If I'm pushing an object across a table, I could be pushing down at an angle, and the bag's moving, or I could come along and push it at this angle, the bag's still moving. I could like push it here. I have to push a lot harder. So the force vector and the velocity vector actually produce a work scalar, or or an energy scalar. Because where'd the thing go? Well, it went from here to here. Did it actually rise? No. Was some work done? Yeah. Take your thermal imaging camera, and you can see that some friction happened, and the energy went somewhere. So energy is the same as work in terms of dimensions. It's force times distance, and its dimensions are mass times length squared over time squared. And then power equals energy divided by time equals force dotted into velocity. So just like, so we obviously, we all know that force is a vector, one normal component. So I'm standing here and my feet are pushing straight down, but they're also keeping me from falling front to back and side to side. So force has those three components.
Would you ever consider calculating the force of gravity into your equation?
That's exactly what that is. That is the force of gravity. Your weight equals the force of gravity. It's exactly what it is. So multiply your mass in kilograms by gravity, which is 9.8 meters per second. That's the force. Yeah. And so just like F equals ma, if you're in a gravitational field, you just replace A with G. And you got your force. Okay. Yeah. Now, power is energy per time. Power is how quickly you consume or convert, since you can't actually consume energy, you can only convert. You can't make energy, you can only push it around. Funnel it, if you will. So power is energy divided by time, so it's how quickly energy is consumed. Power is also force dotted into velocity. So, for example, let's say I want to move this bag across the table. Again, I'm going to push on it with some force. Could be there, could be there, could be there. I mean, there's an infinite number of places I could put a force on this bag. And if my goal is to get it over here, I can do it, very, very hard and fast with a certain amount of power. I could do it slowly. I could get over there eventually. But here's the thing about the dot product. So I could do that and then that, and one of my energy is going into making it rotate instead of the velocity. So velocity is also a vector. Velocity is the direction the thing is moving. So that's power. Power is force dotted into velocity.
So speed is vector, and then force isn't directional, because acceleration isn't directional.
Acceleration is also a vector.
Okay.
It is, acceleration is direct. Speed is a scalar. Speed is the magnitude of the velocity.
Vector is magnitude, so scalar is directional.
Scalar
is magnitude. Scalar is magnitude, and vector is magnitude
and direction. Yep. Okay, so the dimensions of power are mass, and really all we're doing is divided by time. Mass, length squared over time cubed. Okay. Yeah, perfect. So this very first page of the book, we want to talk quantitatively about energy. Neat thing about it, it sits right between those two dimensions. Sort of sits above force, if you will, and sits below power, if you will. And the SI units are the Newton, the joule, and the watt. So a Newton is it's just 1 meter times 1 kilogram divided by 1 second squared. The joule is just a Newton meter. So either lifting something, and a Newton. Here's the kind of easy way to remember. So gravity is 10 meters per second squared. A joule is a Newton meter. So something that weighs 1/10 of a kilogram, something that has a mass of 100 grams, has a weight of about a Newton. Something has a mass of a kilogram weighs about 10 newtons. Pretty easy, just because of the way the units of meters and seconds squared work out. So, we don't really think about weighing things but if you can think of your weight in kilograms, you're probably somewhere between 50 and 100 kilograms. If you think of your weight in kilograms, you can then very quickly convert to newtons by multiplying by 10. Okay, and then a watt is just a joule per second. Now, and again, the neat thing about energy is when we're talking about joules and watts, we can talk about mechanical, electrical, nuclear, electromagnetic, all types of energy, and the watt is basically the rate at which it's converting. So these bulbs over my head, let's see if I can read that. 32 watts.
You really see it?
Yeah, I think so. 32 watts. Got lucky on that one. 32. So each of these fixtures is 100 watts. You would never say I've got 100 watts of light. You'd have to come in, measure the candles or the lumens. But what we know in those lights is that 100 joules of electrical energy is being converted to light every second. Another thing too, we go over this frequently in 101. It's critical that we understand this now. And you hear it all the time in the press. People will say, I burned 10 megajoules I burned 10 megawatts per day. Or that light bulb runs at 100 watts per day. Well, it also runs at 100 watts per hour. It also runs at 100 watts per second. It runs at 100 watts whenever it's turned on. So you never say, in the same way that you wouldn't say, oh, my car drives 60 miles per hour per day. No, you'd say, well, I drove 60 miles in an hour. So power is to velocity as energy is to distance or volume.
Basically, when you say the 100 watts, that's like 100 watts per second, no matter what. So that's why it's not.
You would. It's actually
time, it's
no.
not even per second.
It's 100 joules per second.
Okay, I see.
It's 100 joules per second.
Because joules is energy.
Yeah, 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 yeah. It's 100. If it's a 100 watt bulb, it's doing 100 joules a second. Yeah,
Okay.
yeah, yeah. Okay, and when we talk about electricity, well, so since there's about 10 fixtures in here, the lights in this room are running at about a kilowatt. There it is, right there, 1 kilowatt. kW. It's important to keep that K small and the W large. It's also important when you're writing your units down, the names of the units are always lowercase. Yes?
In the future, we could actually open these blinds and turn the lights off.
We will. We will. We might even do that in the very near future. Okay, so, well, there it is at work. Kilo, mega, giga, tera, peta, exa, zeta, and then yada are next. 300 yada watts coming out of the sun.
That's a lot of watts.
300 yada watts. Okay, we discussed the Newton. There it is, 1 kilogram times 1 meter per second. I wrote this on the board already. Energy is force times distance. We're not going to really do vectors much at all, if at all, in this course, but just for your reference. There's power, the rate at which it's converted. Now, since energy and power can take on many forms, this megawatt equivalent would mean that how much energy is in biomass. So how much biomass would you need to make a megawatt equivalent of a certain energy type, or ton if you're talking about mass, or I'm sorry, thermal if you're talking about thermal. So typically you don't think, usually thermal is measured in BTUs, but so E is for electrical and T is for thermal. Another thing to keep in mind, most houses, most North American homes run at about 1 kilowatt. Average. Okay, another really handy conversion, 1 kilowatt hour is 3.6 megajoules. Super handy. The joule is sort of the standard currency, if you will. I don't know if you want to call it the dollar or the euro or whatever, but we will frequently be using megajoules. There's your tons of coal equivalent, tons of oil equivalent, barrels of oil equivalent, etc. Okay. First law, we'll do a little bit of this and then we'll take a break. First law, thermodynamics. Can't create or destroy energy. Do you guys watch these big physics lectures at all? Where there's dark matter, dark energy, regular matter. So, according to the most recent theories, only about 20% of what we see in the universe is either like regular energy and regular matter. Or it's just like sitting, I don't know, somewhere, I can't see it, but there it is. And it only something like a tiny fraction, 0.5%, is like the periodic table. Because the vast majority of the universe is hydrogen, smaller elements. So we're just we're just the froth. We're just the lucky froth that happens to be conscious. Anyway, so first law, you can't make it, you can't destroy it, it's just there, energy. Okay. So as I said before, you don't really consume it, you just convert it. And typically when we're consuming energy, we're converting chemical energy, biofuel, petroleum, etc., converting chemical energy into mechanical or thermal. There's still, you might think of there being a little bit of chemical energy sitting there in CO2, but the only way to like get that back is to put some more energy into it to break that bond. I mean, that's exactly what sunlight does when it reverses that.
It's like equivalent exchange. And in particular, the amount of water that a human is comprised of is generally around 80%.
Mm-hmm.
And if we're all on the land mass, then you can consider all of that water on top of the land and distributing that weight accordingly. So,
yeah, sure. Yeah.
I don't know.
Yeah. Well, and we much to Kat's chagrin, we do make and break or water bonds all the time.
And not to mention we heat water up to 98 point.
Yeah, that's all thermal rather than chemical, but yeah. So the point is, there are a lot of different forms of energy, and you cannot create it or destroy it. Okay, kinetic. That's more or less what we're talking about here. Things moving through space. Gravitational, lifting something. Electrical. Again, the lights we're looking at here, or nuclear. There's your kinetic energy, 1/2 mv squared. M is obviously mass. Velocity is obviously meters per second. There's your thermal energy. Okay, this is a perfect example of gravitational kinetic energy. Is moving something that weighs about a newton, and that's about an apple, about 1/10 of a kilogram, through 1 meter. And that's just doing 1 joule of work. The same thing here is that, I think they've got, let's see, higher temperature, Kelvin, gravitational. They don't mention it, but one joule of energy is also the energy required to raise 1 gram of water, 1 degree Celsius. So that's how you can convert. So for example, if this apple landed on a gram of water and stopped moving, the gram of water would go up by 1 degree Celsius. I mean, it would absorb that energy in that way. That's exactly what happened. That was the big debate between Kelvin and Joule back in the day. Another very important thing. Voltage is the force as velocity is the current. So right over here I've got power equals E divided by T equals force times velocity. It also equals voltage, big V, times current, I. So, for example, in a hydroelectric dam, that's what's going on. There's water's being forced through the turbine at some velocity. out comes your electrical at some voltage and at some current. Same thing with every wind turbine. Yeah.
So you said voltage is to force as flight is to current?
Voltage is the force as velocity is the current. So the way you typically think of this is that force and voltage are what are called across variables. So think of a suspension bridge. The bridge sort of holds that force across space. Velocity and current are the through variables. They move through space and time. And you can even go on that suspension bridge and run across it. Someone running across would be the electron moving through the wire. Okay, there it is. Power is voltage times current. Nuclear, I don't know if he drops E equals mc squared here. Not really, but we covered E equals mc squared, the relationship between mass and energy. And ultimately, that is where we get our energy from, fusion in the sun, which, bizarrely enough, comes from gravity. Loss of gravitational potential in the sun drives the thermonuclear reactions. Okay, let's take a break there. I think we got about 15 minutes left. We'll be done for the day.